Concrete built the modern world. It is under our roads, inside our bridges, beneath our cities, and wrapped around almost every building we enter. Humans use more of it than almost any material on Earth, second only to water. But the same material holding the world together is also helping heat it up. Cement, the key ingredient in concrete, produces around 8% of global greenhouse gas emissions. Now China claims it has found a way to change concrete at its core, making it stronger, cleaner, and in some buildings, less necessary than ever before. So the question is not whether concrete disappears tomorrow. The real question is whether the world has just found the first serious challenge to concrete's monopoly in modern construction. Watch until the end, because the answer is much bigger than concrete, the material nobody could replace. Concrete did not become the foundation of the modern world by accident. It won because it solved problems almost nothing else could solve at the same time. It was cheap enough to use everywhere, strong enough to hold up skyscrapers, flexible enough to be poured into almost any shape. It could become a bridge, a runway, or the skeleton of an entire city, and once it hardened, it stayed there. That is the quiet genius of concrete. It does not rust like steel. It does not rot like wood. It does not shatter like glass. You mix it, pour it, shape it, and wait. For builders, that simplicity changed everything. For engineers, concrete became something even more valuable, predictable. After more than a century of use, they know how it behaves under pressure, through weather, and across decades. Building codes were written around it, cities were designed with it. And for generations of engineers, concrete became less like a material and more like the default language of construction. That is why replacing it has always been so difficult. The problem was never that no one wanted something better. Researchers tried for years. Some replaced part of the cement with industrial waste like fly ash or slag. Others experimented with alternative binders, cleaner kilns, or carbon capture. Each idea helped at the edges, but none changed the basic reality. The world still needed concrete, and it needed it at a scale almost impossible to imagine. China alone used more cement between 2011 and 2013 than the United States used during the entire 20th century. Not in 50 years, not in 20, in just 2 years. That is what happens when modern infrastructure rises almost all at once. But this is where concrete's greatest strength becomes its greatest weakness. The carbon problem is not just smoke from dirty fuel. It is buried inside the recipe itself. To make cement, limestone has to be heated to extreme temperatures, and when that rock breaks apart, it releases carbon dioxide as a direct chemical byproduct. In other words, the emissions are not just coming from how cement is made, they are coming from the chemistry that makes cement work in the first place. That is why this problem survived for so long. The world was not waiting for a better material because concrete was bad. It was waiting because concrete was almost too good to replace. So China's breakthrough did not begin with a miracle ingredient. It began with a stranger question. What if the future of concrete was not hidden in what we add to it, but in what we do to it before it hardens? The pressure breakthrough. China's answer sounded almost too simple. It did not begin with a new miracle material. It did not depend on an expensive additive. It did not ask builders to abandon the material they already knew how to use. Instead, it focused on one overlooked moment before concrete hardens. Fresh concrete is not the hard gray material we see in bridges, sidewalks, and buildings. Right after mixing, it is still wet, heavy, and unstable, a thick slurry filled with cement, sand, stone, water, trapped air, and millions of tiny, empty spaces. Normally, builders pour it into a mold and wait. Gravity helps the heavier particles settle. Vibration tools shake out some trapped air. Water slowly moves through the mix. And over time, the concrete hardens into whatever shape it was given. That is how the world has made concrete for generations. But the Chinese researchers asked a different question. What if waiting was part of the weakness? Instead of letting fresh concrete settle mostly on its own, they applied mechanical pressure while the mix was still wet and workable. Not a small push, a powerful squeeze, similar to the force inside an industrial hydraulic press. The goal was not to change the ingredients. The goal was to change the internal structure before it locked itself into place. And that pressure changed what was happening inside the material. The cement, sand, and stone particles were forced closer together. Trapped air was pushed out. Excess water had fewer places to hide. The loose internal structure collapsed into something denser, tighter, and far less porous. Imagine the difference between a loose pile of sand and a compressed block of stone. The ingredients may be similar, but the structure is completely different. That difference matters because concrete does not usually fail from one obvious flaw. It fails from tiny weaknesses hidden inside it. Small voids become the starting point for cracks. They let water seep in. They give road salt, seawater, and chemicals a path toward the steel reinforcement buried inside. In cold climates, water trapped in those spaces can freeze, expand, and slowly tear the material apart from within. China's pressure method attacked those weaknesses at the source. By squeezing the concrete before it hardened, the material became more compact. Its internal gaps were reduced. Its weak spots became harder to find. And one of the most fragile parts of concrete, the microscopic boundary where cement paste meets stone aggregate, became stronger. That boundary matters. Inside concrete, stone provides strength, and cement paste holds everything together. But the place where they meet is often the weak link. Under stress, cracks like to begin there. If that zone is loose and porous, the entire structure becomes easier to damage. But under pressure casting, that transition zone tightens. The weak link in the chain becomes harder to break. That is why the test results mattered. The concrete became stronger. It resisted water better. It handled chemical attack better. It performed better against freeze-thaw damage. In the strongest batches, compressive strength rose dramatically compared with standard concrete, and the numbers were not small. In some tests, pressure cast samples showed major reductions in internal voids and sharp gains in compressive strength. For engineers, that matters because concrete is not trusted because it sounds impressive. It is trusted when the numbers repeat. But the most important detail was not just that it worked. The important detail was that it worked without changing the recipe. No exotic material, no rare ingredient, no completely new supply chain. The same basic ingredients, handled differently, produced a better version of one of the most important materials on Earth. That is what makes this breakthrough powerful. If you're enjoying this video, hit like and subscribe for more stories like this. China was not asking the world to throw concrete away overnight. It was asking the world to rethink one step in the process. For more than a century, builders poured concrete and waited for it to become strong. China's breakthrough suggested something different. Strength could be forced into the material before it had the chance to become weak. And that was only the first part of the story. Because while one Chinese breakthrough was trying to make concrete better, another was asking an even more radical question. What if some buildings did not need so much concrete in the first place? The steel system that changes everything. But making concrete stronger was only half the story. China was also asking a more radical question. What if some buildings did not need so much concrete in the first place? That is where B-Core enters the picture. At first, it does not look like something that could challenge one of the most important materials on Earth. It is not massive. It is not thick. It does not look like the heavy slabs and columns people normally associate with strength. It looks almost too thin to trust. But that is the point. B-Core is a steel panel system developed by Broad Group, a Chinese company known for pushing modular construction far beyond what most people expect. Each panel is built from two thin steel skins, separated by a precise internal grid of hollow steel tubes. From the outside, it looks simple. Inside, it works like a carefully engineered lattice, spreading force through structure instead of relying on sheer mass. The idea is closer to aerospace engineering than traditional concrete construction. Aircraft are not strong because they are heavy. They are strong because their frames distribute stress through shape, geometry, and precision. B-Core takes that same logic and brings it into buildings. That matters because concrete has a hidden weakness: weight. A concrete building may be strong, but every floor adds mass. Every wall adds load. Every slab demands support from the structure below. And in an earthquake, that weight becomes dangerous. When the ground shakes, a heavy building has to absorb enormous forces. B-Core changes the equation. Its steel skins handle tension and compression. Its internal tube lattice helps resist bending and twisting. Together, they create panels that can carry serious structural loads while using far less mass than a comparable reinforced concrete slab. That means lighter buildings, faster assembly, less wet concrete poured on site, and less time spent waiting for concrete to cure. This is why B-Core matters beyond one material. It turns part of construction into something closer to manufacturing. Panels can be made in a factory, transported to the site, and locked together with speed and precision. Put next to compression cast concrete, the bigger picture becomes clear. One improves the concrete we still need. The other reduces how much of it some buildings require. And if you watched our previous video about China's futuristic engineering wonders, This is the hidden layer behind that story. Comment China if you want more stories about China's infrastructure breakthroughs. Comment Tech for more world-changing technologies. Concrete is not disappearing. Roads, bridges, dams, tunnels, and foundations will still depend on it, but its monopoly is weakening. And once a material that dominated construction for more than a century starts to look less inevitable, the rest of the world does not just watch. It starts looking for a way in. The world starts copying China. Construction is not an industry that changes quickly. A phone can be redesigned every year. Software can be updated overnight. But bridges, towers, and apartment blocks are different. When a structural material fails, the cost is not just financial. It can be measured in lives. That is why engineers move slowly. Building codes take years to change. Contractors are cautious. Cement companies do not rebuild their production lines because one laboratory result looks promising. So when international interest in China's concrete breakthrough started accelerating, it meant something had changed. First came the research, then came the patents, then came the companies, then came the trials. Engineers in Germany, Japan, South Korea, and the United Kingdom began studying the Chinese work closely. Patent filing started citing the original research. And patents are not casual compliments. They are legal and financial signals. They mean someone believes a technology may be worth protecting, adapting, and commercializing. Then the interest moved beyond universities. That is when the story became harder to ignore. Trials, partnerships, and pilot projects started turning the idea from a Chinese research claim into something the global construction industry had to test for itself. Large construction, cement, and engineering companies began looking for ways to apply the same logic to real projects. In Europe, the appeal was lower carbon prefabricated construction. In Japan, it was cement reduction for dense urban building. In South Korea, B-Core style panels fit into a broader push toward faster, more industrialized smart city construction. The reason was not idealism, it was math. In places where carbon is taxed, capped, or regulated, using less cement can reduce costs immediately. It can lower compliance pressure. It can make projects easier to justify. And even in markets without strict carbon rules, a system that is stronger, lighter, faster to assemble, and less dependent on cement becomes a competitive advantage. That is why this moment feels different from earlier promises about green concrete. For years, researchers tried to make concrete cleaner. Some ideas helped at the margins. Some worked in small tests. But many were too expensive, too complicated, too unfamiliar, or too hard to scale for an industry built on trust and repetition. China's approach had a different kind of power. Compression cast concrete did not ask the world to abandon concrete. It asked builders to improve a process they already understood. B-Core did not ask the industry to stop building. It offered a way to make parts of construction lighter, faster, and more controlled. Together, they attacked the concrete problem from two directions at once. One improves the material the world still depends on. The other reduces how much of that material some buildings need. And once real-world trials began to support the lab results, the story changed again. This was no longer just a Chinese science paper. It was no longer just an impressive demonstration. It was becoming something every major construction market understands. A race. Not just a race to build greener. A race to build cheaper, faster, lighter, and stronger in a world where carbon is becoming a cost and speed is becoming an advantage. And if even a small part of global concrete use starts to change, the next question becomes much bigger. How much of the world could this actually reshape? The race to rebuild construction. At this point, the story stops being about concrete alone. If compression cast concrete and B-Core can work at scale, they do not just change how buildings are made, they change the economics of construction itself. The world pours an almost unimaginable amount of concrete every year. It goes into roads, towers, bridges, and the foundations beneath modern cities. So even a small improvement in how concrete is made becomes enormous once it spreads across the global construction industry. That is why this race matters. If a new process can make concrete stronger while using less cement, the impact is not limited to one bridge or one building. It can reduce emissions across millions of tons of material. It can lower repair costs. It can make structures last longer. And it can reduce dependence on one of the most carbon-heavy ingredients in construction. Then B-Core pushes the idea even further. If some parts of a building can be made lighter, faster, and with less concrete, the construction industry starts moving into a different world. A world where buildings are not only poured on site, but manufactured, shipped, and assembled with more precision. That is the race now forming around construction. Not just a race to build greener, a race to build faster, lighter, cheaper, and stronger. A race to turn one of the slowest industries on Earth into something more industrial, more repeatable, and less dependent on the old concrete formula. But this does not mean the world changes overnight. Buildings are not smartphones. You cannot update a bridge with a software patch. You cannot casually test a structural system that has to carry human lives for decades. Every country that wants to adopt these technologies will need new testing, new standards, and equipment most concrete plants do not yet have. That is the hard part. A breakthrough in a lab is one thing. A global construction standard is something else entirely. Large companies in wealthy countries may move first because they have the money, the regulatory pressure, and the carbon costs to justify the transition. But smaller builders, especially in developing economies, may face a much harder path. They need cheaper and cleaner construction the most, but they may be the least able to afford the shift. So the future of this technology will not be decided by science alone. It will be decided by policy, investment, trust, and speed. By which countries rewrite their codes first, which companies take the risk first, which builders prove it outside the lab first, and which markets realize that carbon is no longer just an environmental issue. It is becoming a construction cost. Concrete is not going away. The world still needs it. Roads, dams, tunnels, bridges, and foundations will still depend on it. But something important is changing. For the first time in generations, concrete is no longer the only obvious answer. The material that built the modern world is facing a new kind of competition, not from one miracle replacement, but from better processes, lighter structures, and industrial methods that could slowly rewrite how cities are built. And once that race begins, the question is no longer whether construction can change. The question is, who gets there first? Concrete is not disappearing tomorrow. It is too useful, too trusted, and too deeply built into the modern world. But that is exactly why this moment matters. Because the future may not be built without concrete, but it may no longer be built around concrete alone. China's work suggests that the next construction revolution may not come from one miracle material. It may come from better processes, lighter structures, and a new way of thinking about how cities are built. And if the material beneath our roads, bridges, and buildings can change, then almost anything can. Like and subscribe for more stories. I'll see you in the next one.